Hello, everyone. Thank you for tuning in to this session, this seminar for IGCP 725. My name is Eli Lazarus. I work at the University of Southampton in the UK. I'm in the School of Geography and Environmental Science there. And this session is about modeling human coastal coupled systems. So I'm going to mostly do my take on how to approach this kind of puzzle, this kind of context. And it's probably about as far away from the cores, from cores to code. It's more code than cores, I suppose, at least in concept. But I hope even the most sedimentological among you can get something out of it. So why study or why model coasts as coupled systems in the first place? And so my orientation to this comes from Peter Half, really, who was a mentor of mine in graduate school. And Peter coined the term neo-geomorphology, or more broadly, the neo-environment. So in where this comes from, and sort of, in the context of this session, really, we live in a time of global rarity of intact coastal regions. So direct anthropogenic pressure is everywhere, all coasts of the world, except the poles, and even there, you can certainly talk about indirect changes related to warming. So essentially, every coast is a human coast. More broadly than that, the people who were thinking about this, who I found very influential, Roger Hooke back in '94 published a very short paper, but an excellent one in GSA Today, that about humans as agents of geomorphic change. And this idea has been around since sort of 19th century geography, but Hooke really went after it like a geologist. And then Roger Hooke's thinking certainly inspired Peter Half, who later on, in a really excellent piece, it was a chapter in a monograph, an edited monograph that came out in 2003, Prediction in Geomorphology. So Peter wrote, "A world dominated by the human-built environment bends the classical rules of natural physical processes. And because it does that, because the human-built environment doesn't behave the same way that natural physical processes of landscape change behave, we have to think about human-built environments and the dynamics of those environments and the way they interact with landscapes as distinct from the rules and tenets and sort of frames of classical geomorphology." So that's why he coined the term neo-geomorphology, and then, again, more broadly after that, talked about the neo-environment. Because if you can talk about it in terms of neo-geomorphology, there's also like neo-ecology and things like that. So he broadened it out. But what that means, and it's a tough thing to say to a cores audience. It's hard to swallow, and as trained as a geologist, it's a provocative thing to say, that what this means is that if the classical rules don't work and you have this distinct discipline, essentially subdiscipline of geomorphology, what it means is that the geologic past is not the key to understanding the anthropogenic present. And so the point of neo-geomorphology, as far as Peter was concerned, was that you have to treat the modern landscape and its dynamics on its own terms. So another person who was doing this at about the same time, or over the same arc of his own career, was Carl Nordstrom at Rutgers. And in 1994, Nordstrom was he was a physical geographer in a geography department at Rutgers, and he in 1994 wrote this, I think is a landmark paper. It's a sleeper, but I think it's a landmark paper. Beaches and Dunes of Human Altered Coasts. This became essentially this was his, more or less his pitch to a publisher. This became a book, that, but the original, the sort of the core of it was published in 94 in Progress in Physical Geography. And Nordstrom argued that human altered coasts are a geomorphic problem. They're distinct from an engineering problem, which was typically how they were regarded. Like, any development on the coast was essentially within the realm of civil engineers to think about, and geomorphologists or physical geographers thought about other things. And Nordstrom's approach that actually human altered coasts are a geomorphic phenomenon in their own right, means that his thinking was evolving in parallel with Hooke, and later on with Peter Half, and Peter certainly was reading both Hooke and Nordstrom at the same time. So it was a really interesting kind of evolution of this sensibility to the coast we live on, but from an unusual perspective, certainly in disciplinary terms, academic disciplinary terms. So Nordstrom pointed out that human altered coasts are created, reshaped, or eliminated to suit human needs, or essentially human altered coasts or human altered coastal features are created, reshaped, or eliminated to suit human needs. These alterations affect the mechanisms of change, freedom of movement, locations of sources and sinks for sediment, internal structure, outward appearance, spatial and temporal scales of landform evolution. That's what makes a human altered coast a geomorphic problem, is that these are geomorphic sensibilities. Like these are the ways in which we think about landscape dynamics, and all of them apply to these landscapes that were driving, earth moving equipment around and redesigning to suit preferences, societal preferences, and so Nordstrom dug deep into this. The work is fantastic, and so this is the context that then sets up essentially what defines a human coastal coupled system. So I'm going to say more broadly what defines a human environmental coupled system, and the examples that I'm going to go through in this session are essentially, they are coastal examples. But again, these broaden out. We're going to talk about a coastal environment, but you can take it to lots of other natural physical environments as well. So to my mind, the most precise and complete definition of a human environmental coupled system, or in their case, they called it a human natural coupled system. But a human environmental coupled system comes from Werner and McNamara, Brad Werner, Dylan McNamara, from a paper in 2007 in Geomorphology. And the definition is effectively this: human landscape coupling should be strongest where fluvial, oceanic, or atmospheric processes render significant stretches of human-occupied land vulnerable to large changes and damage. So in this little clip art diagram on the left side of the screen, I have these are numbered. So essentially 1 is in this case, a coastal stretch of land. In picture 2, that is the same land but human occupied. So now it's covered with hotels and condos, and so this is sort of a typical kind of resort economy coastal locale. So human occupied land, vulnerable to large changes and damage. So part 3 there, picture 3, is the same place but sort of in the with a storm event that's caused a bunch of damage. So we'll get to 4 in the next slide. So again, the coupling should be strongest where fluvial, oceanic, or atmospheric processes render significant stretches of human-occupied land vulnerable to large changes in damage, and where market processes assign value to that land and drive measures to protect it from damage. So because the hotel, the development complexes, the built environment in part 2 there, because that is worth something economically, there is value. Market processes have assigned value to that land, to that built environment. That is going to drive what we see in part 4 there of this little cycle, is that after that gets damaged by some natural process, coastal storm, so that's a hurricane strike, it's these are whatever this coastal environment is naturally subject to. Those market forces are going to drive measures to protect it from damage. So that's reinforcement of that's beach nourishment, that's seawalls, that's all kinds of things that might result in sort of engineering works, coastal engineering works at the beach to protect what we see, to protect that built environment from subsequent damage events. Okay, the definition continues a short bit. These processes typically operate over the human or medium timescales of many years to decades, over which time the landscape becomes vulnerable to change. So landscape in sort of 2 becomes vulnerable to change. So, whatever natural processes are occurring in 1 are still at work in 2. So maybe that's enhanced, maybe that's a period of enhanced erosion, or maybe that's a consequence of subsidence, and so accelerated sea level rise, whatever it might be. Maybe that's an increase in storm intensity over time. So these landscapes become vulnerable to change, and over that same time scale, markets drive investment in structures. So maybe more hotels get built, maybe the resort footprint expands, the built environment expands in some way. Profits from those investments get evaluated. So this is sort of the market doing market things. And sort of between 3 and 4, the market is also responding to changes in conditions. So it's reacting to damage events. It's investing further in hazard mitigation or hazard protection. And so that, I've broken it up in a little bit here, but the paper, the references are all at the end of this talk. That is, to me, the most complete definition of what a human environmental coupled system involves. And so in the examples that I'll show in a short bit, you can get at certain aspects of this large description. Some of them are long time scales. Some of them you can get down to fairly short time scales. But this fundamentally is what is going on in a human coastal coupled system. And we'll talk about the importance of sort of identifying where the feedbacks are. We'll talk about that in a little bit. So if you were going to get started doing your own coupled system model, this is, you're effectively stepping into, you're making a bunch of choices that are grounded in sort of philosophy and approach. So there's no one way to do it. There's no one correct way. I don't want to give that impression at all. What I'm going to talk about is the way that I like to do it, and it is the way that reflects my training, and so that is my bias and my preference. But ultimately, the model you design, the model you create, depends on what the model is for. So design depends on purpose, always. So when you're getting started in making a model of your own, the first thing to think about a lot. So this is like notebook, pen or pencil, cup of coffee, tea, whatever. You're outside the screen, you're not reading anything, you're just thinking about, you're maybe you're going on walks, you're looking at this as intensely as possible. And this is deep thinking time, careful thinking time. What is the phenomenon that you want to model? What is it? The model is a tool. And so with that tool, what do you want to demonstrate? What do you want this model to show people? What do you want this model to deliver? Because it's not going to necessarily show you, it's not going to give you like a kind of wildly unexpected answer. It will help you explore a problem, but it's not going to solve anything for you. So it's really, this is really a design exercise. So is your tool for prediction? If it's for prediction and you're doing a human environmental coupled system model, I would, again, my bias, I would put a massive caveat on prediction and think about what prediction really means in the case of your particular example. Another thing or perhaps I'll go so far as to say probably like a more reasonable goal, maybe more reasonable goal than prediction could be establishing reasonable bounds on a problem. So trying to come up with some reasonable bounds for magnitudes of fluxes, or trying to bound a problem with sort of approximate timescales like that. This kind of model the kind of modeling that I'm going to describe is very well suited for that, or these kinds of problems for their inherent complications. That feels to me feasible, still hard, and probably the most tractable in terms of like a goal on which you can deliver is this a tool for understanding a phenomenon more clearly? And in that case, coupled system modeling is excellent. I refer to these things in many ways as not just these models, but many models as animated thought experiments. So they help you visualize a problem. This is the fourth dimension, because you can watch them in time. It turns these problems into 4D problems, so you can watch how they evolve and you can tinker with things, and they're incredibly useful that way. So, and I'll get to this later on, but if you're using this model to understand a phenomenon more clearly, the other thing that you're doing is you're really trying to learn about something by building it yourself. There are lots of people who are incredibly skilled craftspeople who can build you a bookcase. You can buy one from a flat pack and assemble it yourself, but you learn something different. It's not going to be the prettiest bookcase necessarily, but like you learn a lot from trying to build your own bookcase. And that is still a worthwhile effort to try to do it yourself, to see what the detailed problems involved. And so what this gets to, ultimately, what the tool is for determines, what the model is for determines how complicated a thing you need to make, or how elaborate, maybe is a better word, how elaborate is the model that you need to then start to think about. Do you need to build a VR flight simulator, which is what's there on the left there? Probably not. On the right is a flight simulator that I remember playing. That kind of flight simulator may have all of the pieces that you need for the kind of system that you're interested in exploring. So it doesn't have to be state-of-the-art tech. It just has to suit your needs, and it can look, there's a certain kind of elegance in simplicity sometimes, and it's still worth chasing. So, sort of in more detail on that regard, what I'm getting at in a sideways kind of approach here is the this premise of deliberate simplification. So this is the philosophical difference. So some models and plenty of modeling exercises lend themselves to what's formally referred to as a reductionist approach. So you are modeling every detail. That's this beautiful model train on the left side of the screen here. You're modeling every detail. You can see rivets in the engine, and the wheels have spokes, and it's just this. It's a tiny version of what it looks exactly like the real train version of itself. So a reductionist approach is working from very small scales. It's working sort of up from sort of the smallest tractable scales and going up. The picture at the right is also a train with a couple of cars attached. And you can still see it's a train. You can even see it's a steam engine. And the cars fit together. And it even looks like, based on the way this is put together, it looks like the cargo comes on and off. And you can tell which one is the engine and which one is a car behind it. It is, but so it even has some detail, like there look like there are caps on the wheels or whatever. But for the most part, so this it's still a train, and you recognize it as such, but it has been deliberately simplified. The maker has made choices about its aesthetic and its function that make it, there are no pistons, there are no flywheel, there's nothing, or no cams or anything like that. It's just these axles, wheels on axles, but it rolls, right? Like it does a lot of things that a train will do. And so the deliberate simplification abstracts a whole lot of details that maybe, depending on what you need this train to do, you don't need those things. So, if you just need a model for a really little kid to play with, you probably don't need or necessarily want the super detailed one, right? You want the one that has sort of the maximum effect and allows them to interact with it in a way that is not too fussy and complicated and finicky to hook the cars together and things like that. So deliberate simplification, the quote that I walk around with in my head all the time comes from Chris Paola in Minnesota, who at a lab meeting I was at one time said, "You can always make something more complicated." Absolutely. You can always make it more complicated. You can make this train infinitely more complicated. But when you work in a sort of a space of deliberate simplification, and you think about what it is that you can abstract and still retain the essence of the problem, then there are no mysteries. You can understand exactly and access every working part of this system. You can get at all of the pieces. And the other thing that helps is that connecting simple things is often easier than connecting complicated things. There are just sort of fewer things to go wrong, fewer parts to go astray. And so, you're doing yourself a favor in trying to connect simpler model components than really complicated ones, because even connecting quote unquote simple things is challenging. So the other thing that deliberate simplification plays on, that I'll touch on in a bit here, is, or for a second, is the hierarchy of scales, both in space and time. So in a coastal setting, we have many problems. Unless you're working on granular mechanics, if you're working on sort of beach morphology or estuary morphology, you're working at a scale somewhere between you're somewhere between meters up to a kilometer. When you start looking at alongshore features, larger scale morphologies, you're somewhere between 1 and 10 kilometers. So that's, in this case, what's pictured in the middle there those are alongshore bars. And then So 1 to 10 kilometers, and then you get sort of to, if you're looking at very large, much larger scale coastal features, you might be on the order of 100 kilometers. So the scalar hierarchy is important because when you move sort of up this trio, processes at the smaller scales are creating the morphology that is expressed at larger scales. So, what's happening, the sort of swash, what's happening in the swash is ultimately giving rise to the patterns that we see in these bar formations in the middle scale, and the bar formations are starting to inform sediment transport patterns at the largest scale. It's sort of at the landscape scale. By the same token, the shape of the large-scale landscape is setting the physical context in which the processes at smaller scales must operate. So the shape of the coast is determining essentially, the wave climate that these sort of smaller, more local scale sections of coast experience, and that's going to affect bar patterns, and the bar patterns are going to start to affect, to some degree, the beach morphology that we see at a very local scale, like a walkable scale. But what's important about thinking about a scalar hierarchy is that nonlinearity within the hierarchy is what's going to complicate a reductionist approach. So do you need to, and is it worth trying to go from a granular mechanics scale, starting from granular mechanics, if actually what you want is to model a sandbar? Do you need that level? It's like trying to, the model, the example that I came up with as a student, I didn't come up with it, that lives in my head from when I was a student, was to model wave motion. Do you need to model the mechanics of every water molecule in the wave? No, you don't. So nonlinearity within this hierarchy of scales is going to complicate trying to go from, smallest bottom up. But it helps you determine what to abstract, so what to include and what to leave out when you go to create your model. This factors also into experimental designs. This is talked about in Paol et al. Sort of the unreasonable effectiveness of geomorphic experiments, which is a fantastic paper. Hierarchy of experimental design. So at the top of this, you have, and this is, again, probably most relevant to sedimentology folks, uncertainty and extrapolating to the field. At the top is a full-scale experiment. So it is occurring, all of the things in the lab are happening at the real scales at which they exist, they occur in nature. At the other end, at the bottom, there is high uncertainty, very difficult to extrapolate to the field. Exploratory experiments, which can be hugely informative. So my favorite part, it's a little Easter egg in this paper. Exploratory experiments, harder to extrapolate, but interesting. So my suggestion, certainly in the context of this particular talk, is to mess around and find out, to borrow a favorite meme, and from the internet mess. But so mess around and find out to see, I think a lot of certainly a lot of coupled modeling experiments are kind of in the mess around and find out space. They're exploratory. They might be initially harder to extrapolate, but they will be interesting. Which also brings me to an important note on the difference between complicated and complex. So here we have two pendula. So reviewer number 2, you're going to make a coupled model. You have these two different systems. I'm representing them both as each one is a pendulum. Imagine one is a human system and one's a natural system. Both of these systems in isolation are relatively straightforward. So reviewer number 2, and this is something that I've gotten back. Reviewer number 2, by the way, is always the cranky one. This is feedback that I've received before. So an easy critique of a coupled system model would be that the components of this system are all very well understood. So where is the novelty? And the argument, the case that you're going to have to make essentially, and that the reason building your own is useful, is that simple component, one simple component plus another simple component does not necessarily result in a simple answer, a simple sort of third combination. So imagine, in your coupled model, imagine you put these two components together. So you can put them together in a bunch of different ways. You can have them knock into each other. You could, there are lots of ways to sort of couple this system, I suppose, or at least connect this system. But imagine you put them together as a compound pendulum, a double pendulum. And all of a sudden, you go from, two linear systems in isolation to a very nonlinear system. So this expresses chaos. A very nonlinear system when combined. And that is kind of the threshold that you're after in many coupled system models. This is the result that is, the nonlinear result is the thing that really you're chasing in many cases. So the difference between complicated and complex. So this is I think of Rube Goldberg machines. This is one of my favorite coffee maker examples. This is by an artist a version of this was on the cover of the New Yorker a while back. But this is a coffee maker. So the scientist at the bottom of the screen there has just made herself an espresso. And this is this, unbelievable process that the coffee making involves. There might be couplings in there, but really it's kind of, one thing leads to the next. And there's no, you don't want this to be a nonlinear system because you just want the same volume of coffee to come out at the far end every time, when you turn the little knob. And so you don't want any surprises in that. That needs to be a linear system. So there are many things that you can connect in a human coastal coupled system, but the coupling might be fairly uninteresting from a dynamical point of view. By comparison, you can look at Lorenz's water wheel. I love this example. So it makes a kind of Lorenz attractor. But in this case, for those unfamiliar, you have a water wheel, you have a steady input of water, and you have a bunch of leaky buckets on a water wheel. And by varying aspects of this system, the water wheel will turn clockwise and then reverse and turn counterclockwise under the same forcing. And the pattern that it describes and sort of the duration that it spends turning one way versus another and the speed at which it spins, so it speeds up and it slows down. So its behavior can be described also as it creates something akin to a Lorenz attractor. So the most difficult part of modeling a coupled system is in that step of identifying and then deciding in abstract how to represent the essential feedback in the system, and because that is where all the interesting stuff happens. Okay, 3 examples, and then we'll wrap it up. So these are three human coastal coupled system examples. The first is the one that I have spent a lot of time with, and this is The Dynamics of Human Altered Barriers. This was by Dylan McNamara and Brad Werner. It was published in 2008. And so top left, you have a natural barrier. Right below that, you have densely developed, essentially a resort complex barrier island. And you can represent the system in terms of 2 variables to create a kind of state space. So you can, if you track over time in their model, if a coupled model that's, again, it's a beautiful representation of this kind of system. If you look at barrier elevation on the y-axis and versus barrier width on the x-axis, what they're able to show is that the dynamics of a natural barrier versus a human-altered barrier are very different, and they describe two completely different, completely distinct dynamical attractors. So if you give the model the same initial condition, but imagine it has no built environment on it, there are no people on that island, that will evolve in their model to an attractor described by a higher elevation and a wider, essentially a wider width, cross-shore width. So that, based on the environmental forcing that they give it, that's where this island is going to, that's its preferred mode, and it sort of describes a fairly tight little attractor in that space. On the other hand, once you populate it with resorts, same initial conditions, and then you hit run, what you end up in the human-altered condition is that you get a lower barrier elevation relative to sea level, and the width varies dramatically. It sort of rockets back and forth as a result of intensified erosion countered by intensive beach nourishment. And so the attractor described for the human-altered system has much higher variability. So lower stability, lower resilience to big storm impacts. But this is one of the things that they were able to show with the model that they have, which is essentially that little 4-part picture up top. That is essentially what that model follows through. It animates the dynamics of that relationship. So one that I worked on that followed this work, we looked at coupling beach nourishment with a longshore sediment transport. And so in the top panel, that is what happens according to sort of natural resource economics theory, in that given a set of environmental conditions, a coastal town will find, or there is for them, based on a number of environmental conditions like erosion rate, value of housing stock and things like that, there is essentially an economic optimum. So there is an interval over which that town should nourish their beach forever, for all time. That interval does not change. So based on the condition, the model sort of finds that optimum, and it doesn't deviate from it at all. So the model sort of demonstrates, on the one hand, it will demonstrate the steady state. However, if you perturb it, what we were able to show is essentially if one town, so this is a coastline of a bunch of neighboring towns, so you can't really tell. It looks like one block in the top panel. In the bottom panel, you can see that these towns are actually, they're sort of, they've got little stretches. Each little cell there, once things get going, you can tell that they're little cells along shore. So if one town nourishes out of phase relative to the other ones, that's how we perturb this system. The economic optimum for any given town becomes more or less impossible to isolate. And the result for the whole system is chaotic management. So, nobody wants a chaotic beach nourishment schedule, but that's what we were able to show with this model, is that essentially cooperation across neighboring towns is important, because it can be destabilized because of the way essentially sand is shared along shore. So that was a really fun, relatively straightforward kind of coupling that resulted in a really interesting set of dynamics ultimately. And then a little bit of new work that I'll just show you is process intervention during a hazard event. So this is a model that looks like a retro arcade game, but it's actually a numerical model. It's called Dozer. You can download it, you can play it. What you're looking at is essentially direct intervention in washover processes during a storm event. So in this animation, you're looking at Dozer reshapes a floodplain. It's reshaping the dune line, which is at the top of the screen there. So you're plowing back this washover as it's actively coming onto the road. What you're looking at in this GIF this is me playing the game. So this is just a recording of one game. But by reshaping the floodplain and reshaping the dune line, that is affecting sand flux onto the floodplain, onto the road. That is affecting the flow paths that overwash flow and sand deposition take. Those patterns, so if it's affecting the flow paths of the washover, then that's affecting the patterns of sand deposition, and that's affecting where a dozer goes next. That's affecting my decisions as the bulldozer operator. That determines where I go plow next. So what you're seeing, what's represented here, is a fully coupled human coastal morphodynamic model. It's just happening at a very fast time scale because my actions are changing the shape of the morphology, which is changing the sediment fluxes, which is changing the morphology, which is changing my decisions. So it is a fully coupled model. The difference and what enables it to be simple in this case is that instead of trying to code in all possible behaviors of what a bulldozer might do, I have given action of the bulldozer, I've turned that over to a human player. And so all of the adaptive rules about where the bulldozer goes and why, that's up to the player. So all I have to code is the fact that the bulldozer goes forward, backward, it can turn right and left, the plow goes up or down. But the actions of the bulldozer are now turned over to you, the player, and all kinds of interesting analytics fall out of that. So under the hood of this model, while you play the game, which is the sequence up at the top, there is also a dummy condition that you never see that is, what's happening, a natural condition that is what's happening in the absence of any bulldozer intervention at all. So this allows for a perfect information comparison between predicted and observed conditions, and which is otherwise kind of, that's impossible really in a natural setting. So you're able to reconstruct, there's the world without us, there's what would happen in the absence of any intervention, and then there is the consequence of the intervention. Or then there is the intervention itself, and the consequence is the difference between those things. So this is what's sort of secretly embedded in the model that the player never sees. But what's useful about that is that you can pull out quantitative analytics. So you can look at divergence between between sort of what you'd predict from the natural condition up at the top left versus what you observe in the real condition, which is what you play. That's at the bottom. So you get this divergence from perfect correspondence. And you can track things like washover expression through time. So you can pull out sort of the dynamic allometry of the morphology that you get as a result of what you get in the natural case versus the mess of sand that you get in the human altered case. So there are lots of ways to, it looks like a game, but it's actually a fully expressed numerical model, because all of these tools, you can build these tools into the thing that you make. So I'll wrap it up here. This is Eli's unsolicited modeling advice. Mess around and find out. Exploratory experiments are harder to extrapolate, but they're interesting. This other meme I've got, you aren't doing it wrong if no one knows what you're doing. That's up on my office door. And what you see there is a sticker from Evan Goldstein's laptop. Keep models weird. My suggestion is to build it yourself, make a weird model, and you learn and understand your system by making the model. So, Dylan McNamara's beach nourishment or barrier dynamics model with natural versus human altered, the resort model from 2008, that started because he just wanted to see if he could build it. That was a large part of his motivation. Think really hard about whether your model is coupled or whether you just have something that's connected. And if it's just connected, try to find where that feedback is, if there is one. Remember, you can always make it more complicated. So the hard part is really figuring out how to make it simple, keep it simple, and abstract. Deliberate simplification is tricky, but is achievable. And to do all of that, I suggest reading widely, get inspired by lots of things. Open yourself up to lots of different kinds of literature, lots of kinds of landscape. Get out and about. Or at least have your imagination get out and about. And then so I have at the end of this, I've got a bunch of references appended. Those are there those are there for you, and we'll make sure the organizers make those available. But many thanks to the organizers here for inviting me along, and I hope this has been useful. So many thanks.